Hello everyone, welcome back. So in the last lecture we were talking about stiffness under torsion, and we talked about different kind of cross sections and compare solid shaft with the thin tubes. So we'll continue with that, and now we talk about thin sheet under torsion. And if we take a small piece, a small a sheet with thickness T, and we try to twist. So yes, the way we twist, these are the forces we apply at the ends, and what we realize that, yeah, in one direction we see it will be the the torque applied because of this twisting, the forces we are applying at the far ends corners. So F times L. So this is, if we see from one direction, it will be this. But what we also realize from the other end, it will be also same. So it will be the T will be F times H, and the twist will be the same. So either way is the same. And when you talk about the torsional stiffness or the rotational stiffness, so we talk about the K here. So GK by L, and K is the, as we said, for circular cross sections is a polar moment of inertia, but for non-circular sections it's a different, and we have to refer to the references for that. And for these kind of sections, for thin sheets, what we realize, this K value is 1/3 area of the material we here, which is H times T, and the T square. And then if we talk about the rotational stiffness, where we have to apply the torsional moment M and the deflection, associated deflection phi. So what we find that this will come into picture. So it's a to the power q, and that's how we realize that it's torsionally not rigid and it's a very compliant. So whenever we are using this kind of element in the design, we have to be aware of. And later we realize that the sheets, many times they are used for compliance, not for stiffness. So now if we consider a open profile under torsion, so where we have a tube, but there is a slit. So it's a opening, so along the length. So if that is the case, and if we apply the torsion, the torque at the ends, what we realize that there will be deformation and it will slip. So you can see that even the edges, it will deflect. So it will not remain in the same plane. So actually the plane, the cross section, if we see, they are not in the same plane. And if we compare a open profile tube under torsion, then in that case it's very similar to a thin sheet under torsion. So that's why we compare. And what we realize that if you have this case, again we get this K as 1/3 A mat. A mat is the this one, the area, the actual material, T square, and this is the rotational stiffness, GK by L. So what you realize that, again, if it's a tube but with open profile, it's not torsionally stiff, and under torsion we will we'll find that it's a very compliant. So if you want to compare the two sections, two kind of tubes, so in one we have a closed closed sections, closed tube. And then on the other hand, if we have the open one, so in the longitudinal direction there is a slit, so it's open. And when we compare the stiffness of the two under torsion, what we realize that if it's a close, the entire area, the enclosed area, will come into the picture. On the other hand, if it's open, it's only the material, the area of the material will come into the picture. And if we compare the two, the rotational stiffness of open profile versus the closed tube, what we realize that there is a huge difference. And what we can find here is 1 by 12, and then A material versus A enclosed square. So this square term will make a huge difference, and from there also we can find that what is the implication if there is a cut or if the profile is open. So just to understand that, if we just take one example and take a circular tube, thin tube with the same dimensions, so diameter 100 millimeter and the thickness 1 millimeter, but one is closed and in another one is open. So in this case, if we compare, then the ratio of the areas, A material versus A enclosed, we can easily find that, because in one is a perimeter and multiplied by T for this case, and for the enclosed area is the closed surface area pi d square by 4. So if we do that, what we realize that this A mat versus A n will be 4T by D, and for these dimensions what I mentioned, it will be 1 by 25. And if we plug these values here, what we find that approximately the K open versus K closed profile is a 10 to the power minus 4. So it's a huge number, 10 to the power minus 4. So the open versus the closed, and if we just reverse it, we can see that if it's a closed tube, the rotational stiffness is very, very high. So closed, we can definitely use it as a torsionally stiff member, but if it's open, it's a compliant member. So if it's open and by some means if we can make it close, then what will happen? So I think we should be able to get the same stiffness. So what we have to understand that if it's an open section, it's along the slit, wherever is the opening along the length, they don't remain in the same place, but there is a relative movement. So if we don't allow that, probably we can achieve the same stiffness as the closed tube. So this is what I illustrated here. So stiffening by preventing relative axial movement at the seam. So if we just take thin sheet and wrap it, and we try to apply the torsional load, so try to twist, what will happen at the seam? There will be movement. And yes, definitely it's a compliant member. It's not rigid in torsion. But what happens moment we seize that motion by some means? So for instance, if we just close the end, so just by putting a plate at one of the end and then welding it, what we realize that the relative axial movement we are not allowing, and therefore the torsional stiffness of uh, of this one will be equivalent to the closed profile. So this is one of the way. Of course, I think the length and d, the diameter, that's going to be critical, and maybe in order to avoid any kind of relative axial movement, maybe at few intervals we may have to weld it, tag it so that it doesn't move, and that way we can preserve the torsional stiffness. So even though the member is open, but we can still have a torsional stiffness, higher torsional stiffness, or what we can say, we can achieve the torsional stiffness of a closed section even with the open profile. Another way is we can have this kind of sections at the end. So we can have the thin sheet, and with this kind of profile sawtooth, and when it's rolled, they interlock, and then again, because if it's an interlock, then this movement is not allowed, so it's not possible, and therefore if there is no axial movement at the seam, then even with the open section we can still achieve the stiffness of a closed section. So torsionally stiff shaft rolled from a stamp sheet, and definitely what we see here, if we use a stamp sheet, is the age of manufacturing, the cost, those are involved. If we just try to get tube, closed tube, it might be difficult and costly. But if we use just a stamped sheet and then roll it and get into this configuration, this will be very cost effective, but at the same time we can get a very stiff structure, a stiff tube, torsionally stiff tube, even with the open profile here. So what we have to also understand that even if it's an open profile, and suppose if we uh, seize the relative motion either by locking along the seam or locking the movement at the ends, many times we can achieve higher stiffness or stiffness of the closed sections. And many times these open sections we want because of the manufacturing, the age of production of these kind of sheets. What we also realize that this kind of we have many examples here. So different kind of profiles, and we have many folds, intersections, and if it's more than one, then what happens? They are compliant members in torsion, but by clamping the ends just like this, if we clamp it, we can get a very a stiff member, torsionally stiff member. Uh, so other thing is these profiles are also very good in bending. What happens if we try to twist it? There will be warpage as well because these are thin sections. So I think we have to be aware of. But what happens if we have this kind of cross sections, so profile cross sections with only one folding line? So we can see whether it's a L or plus or cross or T. Here the planes, the folding line, there is only one folding line, and in these cases, even if we clamp from the sides, we cannot stiffen because these are compliant, torsionally compliant, and they do not stiffen even if we repeatedly fix against torsion. So even if we close the ends, we cannot stiffen it. And the obvious reason is under the torsional load, there is no warpage. So many times it stays inner plane, and that's the region. It's a very difficult to stiffen them just by closing the end. So these are compliant members, torsionally compliant, and unlike in the other case, if we have these kind of sections, it's a difficult. What we have to remember that all these profiles, whether one fold or many folds, these kind of sections are very good or very stiff in bending. Torsion, and that's why many times is used, but for torsion we have to be little careful and check. So for if the number of folding lines are more than one, so two or more, in that case we can close the end, or we can seize the motion along the seam, and we can stiffen it. But that may not work with these kind of structures. So if we want to have a stiffer structure out of this, then we have to seize that motion, the rotation motion. And how we can do so? By just putting this bar or truss. So stiffening the torsionally compliant frame. So these are torsionally compliant if you apply a torsional load. So if you try to twist it, it can twist very easily. But moment we do, we can stiffen, because then it will restrict that deformation, and therefore we can achieve higher rotational stiffness. So if we want to use this even tubes, closed tubes, torsion, how to apply the loads? So usually there will be opposite loads applied at the ends, and suppose if it's just like this and you apply load like this, it tends to deform. So what to do? So in that case, so that's what it's saying, preventing tube bending by proper force application at the tube face. So wherever we are applying the force, is very important to close the end. So for instance, here we can put this end plate so that the end cannot move, they cannot deform. So it's a closed, or we can have this diagonal member placed so that it ceases to have this motion. So we have to be careful, and moment we apply a load at the ends, we have to also check how it should be applied. Another very common example and common mistake, I would say, if it's a tube-like column, so many times in the bigger structures, the tube kind of column we used, and for supporting any kind of vertical loads, one can easily make these kind of arrangements and then support the load. So just weld this kind of a thing there, and then put the load. What we realize, that moment you have this kind of force supported on this, is trying to pierce through the surface. And what we realize, that the stiffness here is of the order of T to the power Q. So it's a very thin tube, and normal to the surface, it's not stiff. It can easily pierce through, and it's not good design, because it can easily. So what you can see is, in order to support this load, there will be this kind of force coming on the tube or in the column, and it can easily penetrate and damage it. And there are some examples, the catastrophic failure, and many people died in the past. So I think whenever we have these kind of designs and making these kind of structure, we have to be careful. And if we have to really support some load, I think it's very important to have, so either it should be circumferential. So in this case is here on the edge, so you apply the load, but the loading is circumferential. So right, so forces here. So along the surface, so for circumferential load, the tube is stiff, or it can be in longitudinal direction. So it should be on the other side, and then in order to balance, yes, we'll have this kind of loading coming into the picture. So, and for any kind of loading, it can be better. So I think this is clear no, and even if we want to support any kind of loading on the tube like column, I think we can think of some of these alternatives and check it accordingly. Now next is the box. So many times we like thin sheets we are using, but then we also try to understand what is the stiffness of a box kind of a structure, and what if it's a closed, and if it's a closed, what we realize that is closed from all the sides. So the shear flow, everything, if we see, and if we try to see the torsional stiffness, what we realize that the enclosed volume come into the picture, and it means the stiffness can be very high. But moment is a open box, it's only the, so in this case it will be the material, and in this case if we see, this is the deformations, and the stiffness will be again. So what we realize that only the surface area of the material will come into the picture, and we may not get a very good stiffness. At the same time, we can also look at the design, and since it's a parallelogram structure, what we also realize that parallelogram structure, they are not exactly constrained. There is always a one in the diagonally it can move, and therefore what we realize that moment we try to one load is acting at the end, then what we realize that it's not stiff. So again, we can compare the closed versus the open boxes, and the stiffness. So if there is a load applied at the corner, in both the cases, what we realize that what is the bending stiffness, and here for the closed and the open section, if we compare, and yes, I think the formulation, everything, these are from the references, and in this course we are not so much interested in deriving the relationship, but we just try to use it, and if you want to learn more, we can always refer to the literature and learn from there. So we are just trying to use the formulation, but also trying to understand the phenomena, try to understand the rigidity and the stiffness from the degree of freedom and the constraint point of view. So what we realize that when we try to compare the stiffness, so suppose if we are supporting the open box and the closed box, and supporting only at the corners, what will happen? And it will be clearer from here. So if you compare the bending stiffness, so C closed versus C open, what we realize that it's an enclosed volume versus material volume, and you can see that the enclosed volume will be way higher. And if we just put some numbers here, so for instance LBH is 0.5 millimeter, 0.5 meter, and the thickness is only 3 millimeter. So this is the ratio, and if we compare this again 10 to the power 4 close versus open. So 10 to the power 4 times stiffer moment it gets closed. If it's any one side open, we lose that. So I think it's very important to understand that even if we are using open constructions, we have to find a way to close it. So that is the key learning, and that's what I'm trying to emphasize here. Ki if it's not fully closed, the stiffness will be very low. So we have to find a way to close it somehow so that we can claim, we can get that stiffness, and which is of the order of 10 to the power 4, which is very high. So then, and based on this fact, we have many designs. So even so these are the old designs, but the new design, monocoque design, is all thin sheet metals and all closed, and that's why uh, even with the very little material, we can say that we can get a very stiff design and which is safe for the passengers. And on the other hand, we have the tubular design. So the tubes, closed tubes, can be very good in torsion, and the truss design, we can see truss and tube together, and we can get this kind of vehicle chassis design also. And these days, even the Formula One car, if we closely look at it, is a tubular constructions. So what happens if we have, like for instance, this matchbox kind of thing? So without the inside part, just the outer part, if we are talking about, and if we are applying the torque, what will happen? So it's the same thing, and what is saying relatively short tube, so very small tube, subject to a torque exerted by the two equally large and opposed forces, right? The two ends. So that's how we create the apply the torsional load. And when we do that, what we find that these are not torsionally stiff members, they are very compliant. So there will be deformations, and which is very evident from here. So in this case, what is important is what what we have to do is there is a diagonal deformation and we have to restrict that motion. So if we just connect it diagonally, both the ends, so it's a triangular construction now what we see, and actually is now closed, structurally closed. So no need to put a plate entirely, but just by closing the two ends by a bar, just welding them, I think that is sufficient enough. And going by the same logic, we can also go for the triangular construction. So instead of the parallelopiped one, if we tend to use the plates, what is important is how to close it. So what we see here is we just need to weld the corners. So if we just weld it here, that is sufficient, because then we create a link here, and similarly we just close it here. So just tag one welding, we don't have to weld it all along or the surface, but it's just at those 2 points, and it's very important to understand why it's required there. So I think it's also from a fabrication point of view, and although we have the plate, but essentially what we are trying to do is try to achieve this just by tagging at those corners. There are also different ways to close the end faces, and why it's important is because a closed box is not that useful. So because we want to have access, we want to keep things, and we want to support So we want to have high rigidity, but at the same time we also want access, so that we want to have opening. And for that region, though it's open, but how to close it. So there are various tricks. So like for instance this one, just using the ribs or partially closing it, closing the ends will be also sufficient, or just flanges outside. Moment we do that, it also closes it, closes the end, and we can get the a structurally closed box. Or we can also do, we can place a box inside a box, that will also stiffen it, or we can also thicken it, thicken the sections. So another tube. So how to design using sheet metals, and if you are using steel sheets, so we can use pierce welded torsion beam, or we can do a spot welding, and we can create all these structures, and we can get very good structures out of sheet metals only. So these days a lot of designs, because we want to have lighter structures, but at the same time we wanted to have high stiffness. So we can use this concept to get structures, and we can stiffen it using ribs, using this kind of reinforcements. You can see. So this kind of designs are there. Yes, we have to be careful about this. So if there is a load coming, and it should not pierce through. So if that is the case, then this is how it should be supported. So that, so this may be the stiff member, so cannot penetrate, but here the corner will penetrate. So we have to be careful about that. If we are connecting two pipes or two parallel pipe kind of tubes, how to reinforce, because under this kind of loading it may not be stiff, but we can make it stiff by closing the end. So closing the end will provide the these forces, and it will further reinforce. So there will be no penetration or buckling moment we have that kind of reinforcement. So similar kind of thing, stiff tube. So, suppose if you have this kind of design, so again it's a square cross section, it's open here, but close at the bottom. But what we realize that under torsion, this kind of load, if it's there, then it's a compliant, it tends to deform. So what is the good way is, so two end walls. So how? So top one close, so you can get it circular, but so it's a close from the top, and the bottom is this one. So bottom is also closed from outside. So again, so these are some of the we can say design rules or design cheats to stiffen the structure. So at the end, when we talk about this stiffnesses, what we also need to understand is what is the force transmission, and what is the load path. And if that is the case for any frame, any machine, what is the approach? So for instance, in this case, so earlier design used to be like this, is firmly grounded. So principal force in this direction, and then we can grout it. But suppose if we have this kind of machine, and these are the principal force. So for instance, lathe machine or any machining center, if we have, then what we are worried is about this stiffness, not this. So essentially what we want is the stiffness of the substrates and the tool with respect to each other, and not the structure here, how it's supported. So, it's a very important to understand, and therefore, it's also important to understand what is the load path and what is the strategy. We definitely want to minimize or shorten the load path, and along the load path we may have to stiffen it. We want to have a higher stiffness because of the higher dynamics or higher precision. So, for instance, in this case, the tool post, tooling, whatever is supported, that has to be stiff, not the support. So, what we have to realize that when we are talking about the precision, we have to separate these two. So, the load path and the positioning. So, there are two, and the conventional press, what we can see here, they used to be huge, and both positioning as well as the load, they have the same path. So, the new one, you can have a stiffer structure for the load, and for the motion you have a different mechanism. So, in this way you can decouple and we can achieve high precision. So, we'll stop here today, and we have closed the one module designed for stiffness, and most of the content is from Professor Sumus' book, Design Principles for Precision Mechanisms, from University of Twente, Netherlands. And this is based on the book by Professor Koster, which was in Dutch, and um, earlier predecessor also, and from Phillips, as I mentioned earlier. And these are the foundations uh, where, and that's how all these ASML, Philips, VDL, all these big companies in Netherlands or Demcon, they are building machines for high precision application for semiconductor industry, for a space application, for LIGO application, for gravity measurement kind of things, high-end instruments. So, it's a very important to understand the concept and how to apply these concepts to achieve high precision. And these are the very good books. So, one can always refer to these books. So, one is definitely Design Principles for Precision Mechanisms, but this book by Blonding is also a very good book, easy to read, and very small book, very handy, Elements of Mechanical Design by Skakun. So, if you are interested, definitely you should refer to these books, and I'm covering most of the material in this course from these books only. And I have been teaching for last 10 years here, and I have worked earlier in Netherlands at ASML at University of Twente, and previously in Singapore at A-Star, and work on designing various kind of air bearing stages for different kind of precision applications. So, I'll try to talk about those designs and examples, what we have been practicing, what we are doing in our lab at IIT Delhi. So, next we'll be talking about different kind of compliant mechanisms. So, we'll try to summarize whatever we have discussed till now and how it gets implemented into different kind of compliant mechanisms, flexures, to achieve high precision and better repeatable system. So, we'll talk about those system one by one from the next week. Thank you.